In today's lab, we'll introduce concepts of respiration, vital in commercial horticulture, but not covered as a lecture topic. In addition to getting a hands-on or visual sense of respiration by measuring carbon dioxide evolution and oxygen consumption, you'll gain some insight into how respiration dictates the best practices in commercial horticulture from farm to fork. These losses are a big deal. They're not trivial at all. Estimates are that worldwide, about 40 to 50% of healthy fresh produce foods are never eaten. They're wasted from respiration losses, desiccation, and associated invitations for decay organisms. We're going to spend some time on this slide. Consider respiration by the plant as the opposite process of photosynthesis that you learned in lecture. Or in fact, consider that respiration is the whole purpose of photosynthesis by plants. Respiration occurs in the mitochondrial organelle of the living cells of all life forms. Respiration is aerobic. It occurs in the presence of oxygen. Heat is also produced during respiration, biological heat, that adds to the burden on the crop of already heating conditions like the sunlight energy heating ripe fruit or veggies in the field, and heat of respiration adds to the physical heat of produce that it gains when it's carried in trucks and subject to conditions like road friction or sun beating on the trailer walls. All these conspire to reduce shelf life. When we use the word oxidation, as I've described in lecture, what we really mean is that the molecules are losing electrons as the chemical bonds are broken. Hopefully, I mentioned in lecture that you should always remember, now in the future, the expression oil rig. Oxidation is loss of electrons, oil. Reduction is gain of electrons, rig, oil rig. Rust oxidation on metal surfaces that are losing electrons with water, and the metal pits and loses material. While it's not biological, rust isn't different than plant sugar being lost during respiration and weight of the crop being lost as carbon dioxide and as water vapor. Solid dry weight is gone. Sugar production by photosynthesis is reduction of carbon dioxide, RIG. The CO2 gains electrons. So remember oil rig the rest of your undergraduate life to do well in other classes. By the way, respiration has about 16 enzyme reaction steps that you certainly don't need to know or memorize for this class unless you're a crop scientist or you work in human health or have a tortuous love for biochemistry. When I was a college student, we all had to memorize the 16 steps during our senior year of college biochemistry, and that was nearly 40 years ago. It was torture that turned out to be useful in my career. Wine fermentation is oxidation, for example, and wine development in the bottle includes reduction. Sugars like glucose, that is the most common molecule broken down to make ATP energy, makes about 4 calories per milligram of sugar. That's about 36 ATP from a milligram of glucose in the plant or in your muscle mitochondria. Ditto for plants breaking down fats or lipids to make energy, yielding about twice as much energy per milligram, but of course they don't really want to do that, and neither do you. Plants also infrequently break down protein for producing energy, about the same amount per milligram as sugar. It's so true that the moment a crop is picked, it begins to die. Living organisms need energy continuously. When energy stops flowing in the plant, or in us, death soon follows. The higher the temperature, the faster the respiration rate. The faster the respiration rate, the faster death occurs. What does this chart indicate to you? A relatively small rise in the temperature or equally small drop in temperature causes a large increase or decrease in respiration rate. First and foremost, small changes in the temperature have a large impact on that respiration rate as measured by the CO2 evolution. The respiration rate controls the length of marketable, usable shelf life. It controls whether someone who pays for a perishable produce crop gets to consume it or must dispose of it in the recycling bin from the refrigerator. Below 40 degrees Fahrenheit is a typical temperature for refrigerators or coolers. Respiration is low. Home refrigerators likely have a set point of, let's say, 36 to 38 degrees, while commercial storage of produce is just above freezing for crops that need it, and in the 40s or 50s for chilling sensitive crops like snap bean or pepper. Here's the key take-home interpretation of the previous graph. In the typical middle range of temperatures where plants and people typically live, look at the amount of CO2 evolved for every 10 degree Fahrenheit rise or fall in temperature. For every modest 10 degree increase, the respiration rate doubles. Of course, this means the respiration rate drops by half for every 10 degree decrease in temperature. A doubling or halving for a 10 degree change in temperature equals a Q10 of 2. Crops and part of crops that we harvest, ship, store, sell, and consume differ in their Q10 values. A sweet potato that we bake and eat is a dormant sugar storage root organ. It's not rapidly growing and has a low growth rate and a low respiration rate compared with, say, an asparagus shoot in the spring that is growing 6 inches or more per day, or a fresh ear of sweet corn. The crop management and agribusiness management take-home message to you is clear. Get the harvest product temperature down as quickly and efficiently as possible to extend its marketable shelf life quality all the way to consumption when people are eating it. These are self-evident statements to take to heart if you enter any segment of the perishables food industry after graduation. You never know where you'll land, whether it's hospitality food distribution to hotels, schools, or groceries, or in transportation and logistics. After harvest, the plant's needs don't matter anymore. We're no longer growing it. Our needs matter, and that means awareness of respiration losses. I wrote this equation in its unreduced state to accurately reflect that respiring produce loses weight and money as sugars are consumed, and that the crop loses its water from the warm produce as water vapor. When the water vapor goes, the crop loses weight, but it also shows desiccation shrinkage, making it unmarketable and unappealing to eat. Slow respiration down. Produce already has its own metabolic heat of respiration. Like you performing an athletic event, the last thing a grower wants to do is add a field heat load to the equation, driving temperature higher and respiration higher. Many of these practices seem like common sense, like harvesting wine grape or sweet corn in the early morning, or not leaving harvested produce loaded on a truck in the sun even for 10 or 20 minutes. But when people are busy and tense working in a farming operation, common sense is not always common. Workers need to be trained to these practices. Some practices are more sophisticated, like imposing modified atmosphere storage where O2 is scrubbed with charcoal filtration systems, for example, apple storage, or storage and packaging where carbon dioxide is pumped in controlled amounts. Too high and you damage the crop. Too low and no effect. Just right and you put a reduced respiration blanket on the harvested perishable produce that extends its marketable quality shelf life. There's a whole practical applied industry practice like HVAC refrigeration technicians and the underlying respiration science all working behind the scenes. Growers and shippers certainly can't control what perishable food retailers do after harvest in their warehousing and shipping to reduce respiration. But there is tremendous industry collaboration that's implemented to protect the quality and prevent losses. It's called the cold chain of custody and implements specifications for shipping and handling. Because everyone in the produce industry loses together and everyone wins together when temperature and hence quality are protected. Growers and shippers certainly also can't control what people do in the privacy of their own refrigerator. A lot of post-harvest losses occur after purchase at the home level in the produce drawer of the fridge. For every perishable harvested crop, and even less perishable commodities like potato, onion, or sweet potato, there is a best temperature, relative humidity, packaging, and transport handling guide. There are some crops with such extraordinary high post-harvest respiration that they benefit from chilled water contact to rapidly remove field heat and prevent desiccation weight loss. Think of the HVAC and the physics this way. Ice water chills things a heck of a lot quicker than air conditioning because of direct conduct conduction. Some crops hold their best after contact with cold water-free moisture during the packing. This cooling treatment would contribute to excessive rot loss from microbe pathogens on other crops, let's say like little sprouts or mushrooms. Every crop has its own best method.